Let's take a look at some new malware uploaded to Malware Bazaar. So this has been uploaded by an anonymous user, and they state that the password is 2024. They also provide a little bit more context. So we can see that this has been downloaded from GitHub, and it looks like it's a repository posing as TurboTax activation. So TurboTax is a piece of software in the United States that you can purchase, and that will allow you to do your taxes easier, as far as I know. I'm not from the US. If we actually review this repository, it does look like it's a user account that's just spamming the about section with information saying TurboTax, TurboTax crack, TurboTax download, TurboTax tools, etc, etc. It states that the activation requires internet connection, and it also states that the script applies the registry lock method to activate. Obviously, I don't know what this is, and it requires internet at the time of activation. So this is a bit of a red flag in itself, right? Any type of malware or Trojan or information stealer, if it goes off, is going to want to have internet connection. Otherwise, the attacker's not going to be able to get the information. Now, something else suspicious is that if you highlight over this download, you will see that it's actually pointing to a completely different GitHub user account and a completely different repository. And if we look at that, even as of 1 hour ago, there has been a new version that has been released. So we now have this version that has been updated that has the password 2024, and it is version 1.8.4 by this user Witch12138. And once again, this is linked from the user Cross-Undefined Hans. This is likely controlled by the same threat actor. You will notice that this has 59 forks and 25 stars at the time of video, which is actually getting quite high for this cracked software, particularly considering it contains malware. So let's actually dive into this and see what it contains. So I've gone ahead and downloaded both of these. On the left-hand side, we have version 1.8.2, and on the right-hand side, we have version 1.8.4. The actual DLLs in this directory and files seem similar in both instances. There is mention of a keygen, a key file, icon engine, and even license terms, and all of this seems the same, but what seems completely different is the actual setup file. So on the left-hand side, we can see that this one has the big shield, indicating that it's going to prompt the user with UAC to say, hey, do you want to give this admin rights? And we can actually highlight over this and see that it doesn't really have any information. It is also a stock icon, whereas on the right-hand side, we have an icon that is the cat from GitHub, the Octocat, and we also see that there is this AnyMP4 Studio is the company, which is completely bizarre because this is supposed to be nothing to do with MP4 software. There is a good chance that this is going to be the executable that's actually malicious. Now, I want to get an idea of the capability of both of these. So the first thing I'm going to do is just look at the imports. So I've gone ahead and used PEBear, and I've loaded in version 1.8.2 and the new 1.8.4. The first thing that I see is that both of them seem to have a BSS section. However, one of these BSS sections seem different to the other. BSS in itself is a normal section on PE binaries, but on this one, it seems to have an uppercase, which is a little bit strange. So if we look at the imports on both binaries, we can see that the first one only imports kernel32.dll, and it has a number of imported functions. The second one, however, imports kernel32.dll and msvcrt.dll. So this looks like it's been created in a different way, and the sizes are completely different as well. One of these is quite large at 30 megabytes and created with inno setup, whereas the other one is only about 500 kilobytes. What we will notice is that on both of them, they have indications that injection is going to be performed. So on this one, we can see virtual alloc, virtual protect being called. We can see suspend thread as well. And we can see resume thread, and we can see create thread. But we don't actually see create process, for example. That could be used to spawn a process, create a new thread in that, overwrite that thread, and run the malware. So what we actually have is a case where it looks like injection's being performed on this one. And if we look at the other one, we do also see virtual alloc again, but we see a lot less of some of the other imports that we saw. It is quite possible that there is injection going on where these APIs aren't being seen, that they are being called indirectly and not directly imported to the executable in this way. It could be using alternate versions, so it might be using NT-resume thread or NT-create process or ZW-create process as opposed to create process. So these are all things that we need to keep in mind when we're doing some sort of analysis, but it does look like it's performing injection. So what I want want to do is confirm that this is likely going to be injecting into another process. Now, there's a couple of ways that we can do this. We could use procmon, we could use process hacker, we could just keep an eye on processes to see whether anything new spawns. And to do that, I'm going to use a bit of a obscure manner, but it will work. And I just find it a little bit interesting to actually tap into Windows telemetry. So what I'm going to do is I'm going to create a PowerShell script, and this is going to subscribe to a CimIndication event. And from that, I can then make an action occur. And so this is going to essentially be waiting, listening for indications that a new process has started, and then I'm going to use that to actually tell me what process has started. So let's dive into a PowerShell script and do this. So I've created a PowerShell script, and I'm just going to walk through what it's essentially doing. The first line isn't going to do anything unless we've actually run this before. What it's trying to do is to unregister the CimIndication event that we've registered. Now, what is a CimIndication event? Like I said, you can subscribe to anything to do with Windows management instrumentation and actually get notified when things occur. So for example, you could actually subscribe and understand when a registry modification event occurs or a process starts, which is what we're going to do here. So the action is defining what we want to occur when this new process has started. So in this case, I'm going to be monitoring for all processes that start, and I just want it to essentially write those details to the console here.
Hi everyone, it's Jai here from the future. If you are playing around with registering CimIndication events, do not make it so that when you are tracking new processes created, that you spawn a new process. Because if you don't have some filter here on that action taking place, you may end up in a world of hurt. I'll leave a clip here that shows my experience with that. So we run the script, it does look like it's set to run. There's nothing in this directory yet. If I run calculator or something, yes. Oh no. Oh dear God. Oh God. Oh dear God. Oh no. Oh no. Oh no. It's triggering on itself. Oh no. What have I done? Oh boy. Oh boy. Oh no. Oh no. We need to kill this process. We need to kill this. We need to kill this. Oh my goodness. I have got a variable that's defined as name, and one of the things that's exposed through this register CimIndication event is the event variable, and from that you can actually derive the process name, the process ID, parent process ID, and a bit more information. But they're the main ones that I'm interested in. But what it doesn't expose is information such as the command line or the parent process name. It only has the parent process ID. So what I've done is I've gone and got a little bit more telemetry with PowerShell here, in that after this occurs, I'm just going to be extracting the command line based on the process ID, so we understand the command line of the process that's run as well. Then I'm also going to get the parent process name based on the identifier, so the process ID that has spawned here as well. And I'm basically just using the getCim instance, using the Win32 process, and then I'm specifying that the process ID has to be equal to the parent process ID that was exposed in our CIM callback. So then we also will just get the command line associated with the parent process as well. I could get the parent process name, but I've gone with the command line at this point in time. What I'm going to do is actually just run this, and straight away you'll notice, okay, it says that this process started doesn't exist. That's because it tried to unregister something that doesn't exist. But if we don't have this in and we've run this before, we're going to get clashes with it trying to create a new source identifier, so a new trace with the name process started, when there is already one called process started here. So it's currently running, and it's just keeping an eye on processes that run. So if I was to open up something like the calculator on Windows, you will notice that my terminal now gets populated, and it does show, okay, a new process has started. DCOM has launched calculator. Then we also see all these other processes that are happening, and they're just things that are occurring in the background on my Windows operating system. So one of the things that I want to do now is actually run the malware. That's going to give me a bit of an idea on whether that malware is spawning any other processes. I'm going to do it for both because we've got a bit of an idea of the parent process situation here, so I should be able to run both pieces of malware and see what's happening. So I'm going to run setup.exe. You'll see consent spawns because that's the UAC prompt on Windows. If you see consent.exe, it means that a UAC prompt has popped up. And then we can see that regasm.exe runs. So that's a bit interesting. You'll notice that it didn't actually capture the command line information as well. So there's a good chance that this actually ran so quickly and terminated that we don't actually get any idea on the parent process or the current command line of this. So there's a good chance that
that that is going to be injected into. So it does look like this is injecting into the process regasm.exe, and I really want to understand what that is. But let's look at the second variant to see if it's any different. So I run the second variant, we can see that it launched from explorer.exe, and at the moment, it doesn't look like anything's occurred. But malware authors are a bit tricky. They may have included some sort of timeout or some sort of delay. Oh, and now straight away we see BitLockerToGo.exe spawns. So now we have an indication that BitLockerToGo is likely being injected into here. And we see that same thing where it's not getting the command line. So it actually ran so quickly that we weren't able to execute this next part of the PowerShell because there is a ever so slight delay when you run a process. I think it's about a second. So you run a process and a second later you get that callback. So from that CimIndication event, that notifies that the process has run, but there is that 1 second delay. But we can see that BitLockerToGo has spawned as well. So these are the two processes that I really want to focus my efforts because it does look like it's injecting into these two different processes. And exactly what it's injecting into it, we don't know yet. So let's dive in. The first thing to know is that setup.exe here is a 32-bit process. The other version is a 64-bit process. So that tells us that one of these is going to be running 64-bit operating system code and the other is 32-bit operating system code. And all that does is mean that we have to use probably the right tool for the job to make sure that we are debugging in 32-bit version or 64-bit version respectively. So for the first one, I'm going to use x32 debug. And what I'm going to do is I'm going to spawn the process. So selected setup, and I want to include some breakpoints. The breakpoints that I'm really interested in here, because we didn't see any indication of particular APIs being used, I want to know if I can add a breakpoint to something like nt resume thread, because resuming the thread is what's going to happen if certain types of injection is occurring. So let's do breakpoint on nt resume thread, and it looks like it has added a breakpoint. And the other thing is that it might be using create process, but it's not using create process imported. So maybe it's using nt create process or zw create process. So I'm going to create breakpoints on that as well. So we got one on nt create process, and we got one on zw create process. So we've got zw create process, nt resume thread, and that is also accounting for the nt create process there as well. So let's give this a bit of a whirl. I'm going to run the malware, and we are at the entry breakpoint. I'm going to click continue. We can see, okay, it's now hit a breakpoint at nt resume thread. We can actually look to see if regasm has spawned, and it looks like regasm has actually spawned. So we can see this new process has started, and we actually captured the parent command line in this case. So now we've got a case where it's spawned and it's right before the thread is resumed. So let's actually take a bit of a look at that process, because that might actually now contain the payload in its memory. So I really want to use one of the plugins that is included within Flare VM and is very useful, which is Scylla. So if we use plugins and we use Scylla, one of the things that we can do is actually choose the process we're interested in. So we can see a bunch of different processes. In this case, it is regasm.exe. And if we click file, we can look at dumping specific memory or specific sections. So if we go dump memory and take a look, we can actually see that one part of the memory at addressed 0x400,000, it is actually set with execute read write. If this is execute read write, there's a good chance that this is the section of memory that has been injected into, because without the ability to read, write, and execute a particular section in memory, you're not going to be able to actually inject your payload. And there is actually this dump PE that we can use here, which makes this really quite useful. So I'm going to specify this address and hit dump PE, and I'm going to save this to regasm.dump.exe. And now if I look on the desktop, there does seem to be 306 kilobyte file, which is regasm.dump.exe. This might actually be the injected code. One of the things that I'm going to do is run fakenet, because I want to understand whether this has been dumped in an executable format that I can actually run or not. And if I do run it and it has been dumped in that format, does it make any kind of network connections? We could have done this dynamic analysis to begin with, but I've decided to be a little bit of a pain here and do it in this way. So now that we've got this dumped, let's see. Ooh, interesting. We've now run the dumped process and it says,
"Do you want a
run a malware. Now, this is actually a good sign that this is going to be Luma C2, because Luma C2 enforces a cryptor on people that are using the malware. So if it isn't packed and encrypted in some kind of way, shape, or form, and is running in its raw format like this, it prompts with the message, do you want to run a malware? Now, I'm a bit of a daredevil, so I want to run the malware. And straight away, you'll notice that it makes a number of connections. So there is a DNS request for this PW domain. We do see a bunch of .shop domains that it's connected back to as well. So these seem to be the command and control domains associated with this malware. So now we've got possibility that this is Luma malware, but we're still not 100% sure. One of the things that we can do is use FLOSS, which is the Flare Obfuscated String Solver. And this is created by the team at Flare, the FireEye Labs Advanced Reverse Engineering team. So let's actually give this a shot. I'm going to specify FLOSS against regasm dump.exe. Now, FLOSS, it can be seen as strings on steroids in that it's going to be getting a lot more information than just the strings binary will get. It's going to understand some of the obfuscated strings that are being built on the stack, and it's also going to bring some of them to light as well. So it's really quite a powerful tool created by the team. So let's see what comes back using the FLOSS utility against this now dumped binary. And we can begin to see stuff that looks like user agent strings. We can begin to see stuff that looks like it's targeting Thunderbird and Steam. And we do see this mention of configuration, this buy now on Telegram, that is Luma no work. And there seems to be a Luma C2 build that is May 25th, 2024. So this now gives us a good idea that this is actually the Luma C2 stealer. We know that this is targeting Discord, and we can see that it's targeting Valve, so it's targeting Steam, and probably a bunch of other things that we were able to pull out from this binary. Of interest, Luma C2 does generally have a Tesla browser user agent. However, it does look like maybe this is changed in later builds or is customizable, because we see a static string mentioned for the user agent that is no longer something that is severely obvious to us. Nonetheless, it does look like the end result of this cracked piece of software, at least the previous version, is dumping Luma Stealer into memory. And then that's going to go and steal parts of information from your system. It's going to steal your passwords, your credentials, your sessions, anything else. So let's take a look at now the second version and see if it's any different. This time I'm going to open up x64 debug, because this one is a 64-bit executable as opposed to a 32-bit executable. So I'm going to use the write tool for the job. So I'm going to go ahead and open up that next version, this git softwares, and this setup version. Now, once again, we might need to define some breakpoints because we haven't actually got the breakpoint set for the process injection that's likely going to be occurring. But in this case, we did have things that were a bit more common. So we could probably do it on resume thread. Maybe we can do nt create process, and it does look like that's there as well. So now let's go ahead and run this malware and see whether we capture anything or it breaks at the right moment to figure out what's going to be dropped into this process memory. Remember that this one is actually going to be connecting through the BitLockerToGo executable as opposed to the regasm executable. So I'm going to go ahead and run the malware, and it does look like we have probably the initial TLS callbacks. That's fine. Let's get through that. The entry breakpoint, let's get through that. And now we've hit resume thread. Let's see if any process has spawned. And in this case, it doesn't look like a new process has spawned yet. So we haven't actually seen evidence of that BitLockerToGo spawning. I am just going to use the plugin Scylla and see if we have anything running. And it doesn't look like we do. That is the BitLockerToGo. I'm also going to confirm that this isn't a 32-bit process, and it also doesn't look like it's run yet. So let's continue running the malware. Remembering that there was actually a bit of time that we had to wait before the BitLocker process ran.
3 hours later.
And so I can actually see that this BitLocker discovery volume contents BitLockerToGo executable has now spawned. And we've hit a breakpoint on that resume thread as well. So there's a good chance that this has actually been injected into, but it may not have been. The only way we'll know is if we actually dump it and take a look. Once again, I've got Scylla open, but this is Scylla in the 32-bit version. So we did have a 64-bit executable, and as part of the unpacking and injection routine is injecting into a 32-bit process. So we do have to use the Scylla x86 version that's within the x32 debug as opposed to the x64 debug. So I'm going to dump BitLockerToGo, I'm going to dump the memory, and let's see if we've got any kind of execute read write. So we've got execute read and we've got execute read write here. And I'm just going to name it BitLocker.ToGo.exe. It has an invalid PE file or invalid PE header. Try reading PE header from the disk/process. And so a useful tool that we can use here is Process Hacker. I've actually opened up the BitLockerToGo memory space here, and we can see that there is that read write execute, and this is about 352 kilobytes that has actually been allocated to this, which gives us an idea that this is around the same size of the injected payload that we saw before. But the difference is, if we actually look at this, we will see the memory space is empty. So there is absolutely no bytes that are currently within this process memory space. So this gives us a bit of an idea that it hasn't yet wrote the bytes to memory. And we're going to need the bytes to be written to memory, otherwise we're not going to be able to dump this from memory. So what I'm going to do is see if I can create a breakpoint on write process memory, and it says that I have been able to do that. So let's actually run the malware again, resume thread. We keep hitting resume thread. You can see the hits go up as we do this. I'm actually going to disable that for the point in time and resume. And it does look like we've actually hit write process memory. Now there's a good chance that what it's doing is writing those bytes so that it can be injected into that process. And if we actually look and we follow this in dump, we can see that there is an MZ header that is going to be written to the process memory. So this is likely the entirety of that. And what I can do is, before it resumes that thread, we can actually now enable the resume thread breakpoint again. We're going to enable that. We're going to step over this function so it writes the processes to the memory space. So we can see that in the call here, where it's writing those process bytes, it's writing them to this 28B with all the zeros. And we know that this is actually the base address that we were going to have our bytes written to. So this is what was empty, that 28B with all the zeros. So now it's going to be writing those bytes into this process memory. It hasn't done it yet, as we can see here. So there are some calls. We can see NT query virtual memory here. But now that the call to NT write virtual memory has been called, so we could create a breakpoint on that in the future as well, we do actually see that the bytes have been written into the BitLockerToGo process memory. So we have that MZ header and we have all the bytes here. So now what we can do is actually dump that, because that's really what we want, because that is the PE file. Now we can use the same thing. We can use Scylla in order to do this. We could probably even do it here by basically just specifying save, or actually going in and copying the entirety of this file. So we can say this is the BitLockerToGo and replace it. And now we actually have 352 bytes on the endpoint. This isn't necessarily the PE file. There might be other parts in this memory that's allocated that are actually not part of the PE file. If we were to use something like Scylla, so with the 32-bit, we go plugins, we go Scylla, we specify the BitLockerToGo process, then we go file, dump memory, and we find that memory that we had that has execute read write, which is this one, page execute read write. We do that dump PE, and we actually specify this as the BitLockerToGo executable. We're going to name it the dump so we know. And now we've actually dumped that file. And if we look on the endpoint, this is actually 305 kilobytes. So you can see the difference between dumping it just manually through Process Hacker in that way and actually dumping it through something like Scylla. Now we actually have the dump here. Let's see if it is the same.
Do you want to
Run a malware. Now we've got a good idea that this is actually running probably the same malware, Luma C2, and we've still got FakeNet running, as we can see here. If we actually run the malware, we can see connections back to the same C2 domains that we saw before. And I'm sure if we actually ran a command prompt and ran FLOSS on this, we would probably find that this is the exact same payload that was in version 1.8.2, except this is the version 1.8.4, still delivering the same malware and not actually being this cracked software. And we can see the similar things. We can see a similar user agent. We can see also here evidence of stealing cookies from web browsers. We can see stealing emails, Discord mentioned, this clipboard.txt. We can see Luma C2 built on the exact same day. So it is the same malware build here. And we can actually see that it's extracted some C2 information. So one of the domains, the catlack jelly odwps.shop, has actually come out now with FLOSS and all this other information. So we've got a good idea that this is deploying Luma C2 into the memory as well here. We could actually monitor the API calls to get more information about where this is connecting back to. We know that this is connecting back to the domain, but there is actually something that it would want to post to that domain or make a GET request to a particular URL endpoint. We can actually look and see that both of these files are 32-bit. So we have a 32-bit payload here, and we have a 32-bit payload here. So one of the tools I want to use is API Monitor. Now, API Monitor is a fantastic tool that's created that is quite powerful in that it's able to monitor different API calls that an executable makes and what's being passed to those API calls. You will have to enable whatever you want on the left-hand side here. For a starting point, I like to enable everything just so that I can start with all the information and filter back as opposed to missing something. Now I can choose a process to monitor, and I want to monitor the reg.asm and then also the BitLockerToGo dumps because they are what we've dumped from the process memory, and we are able to actually just run these because we've dumped them correct. So let's say we want to do reg.asm dump. Do you want to run a malware? Yes, thank you. I want to build that snowman. Now I'm also going to choose the BitLockerToGo dump, and I want to run a malware. And you'll see that the calls have stopped very quickly. So even though this is the malware, there is a good chance that this does what it needs to do and stops, terminates, and that's what we actually saw in the behavior in the initial aspects of our analysis. So if I take a look at the API calls, we can see that there are standard reads on different things. There's a lot on this app help, so I am going to filter out this. I'm going to just go exclude, and I'm going to exclude the API calling module name. Yeah, let's do the calling module name. So we can see the loading of particular DLLs, and this kind of Unicode string is going to allow us to get a lot more information when we're doing analysis in this fashion. Once again, we can see share cred with HTTP. This has all come through this RTL init Unicode string. So I might actually want to just include that API. Let's include that API name, and straight away we get more information on what may be happening. But it hasn't actually given us the C2 information. So now we might actually need to change our filter just a little bit to get that back. And so the way to do that is we can go filter, and we can look at our display filter, and we can just clear that and say, yes, clear that filter, and we're back to starting point. Now, because we actually did see the C2 domains, and we want to get that information, let's actually look for those. One of those connected to this relactionfluor.shop. What I'm going to do is I'm going to do a find, and we're going to look for that. And we actually found it pretty quickly. And so this is using the IPv4 string to address EXW. So there seems to be checking to see IPv4 and IPv6 addresses. We could actually filter just based on that, or we could actually only include that module. So the module that we have here is the winhttp.dll, which is a bit interesting. So I'm just going to include that. And straight away we see all of the C2 domains here, but we don't see exactly what it's connecting back to. And so if I clear my display filter here now, you can see this RTL Unicode to UTF-8N. Now this is more interesting. If I was to only include this, let's say this API, now we can actually see evidence of the endpoints that this is connecting back to. So we can see that it is connecting back to this /API, and that is consistent across all of the activity that we see here. And we see the same on the other execution. So now we have a good idea on what this is connecting back to, and also the command and control domains associated with these malware. And we also know that it's being injected into two different processes, reg.asm.exe and the BitLockerToGo executable. We also had a bit of fun using CimIndication Events to notify when a process starts. But that's it. That's all I wanted to show you today. Thanks so much for sticking in. Please give us a like, subscribe. The video's free, didn't cost you anything. If you have any thoughts, feelings, comments, anything else, please leave them in the comment section below, and I will catch you next time.